talk about common emitter amplifier, before we talk about common emitter amplifier, we would see basically some details about an amplifier. Now, amplifier, when we talk about an amplifier, generally we mean a voltage amplifier, but actually there are 4 types of amplifiers. Now, you can think of amplifier as a controlled source. So, you have 4 types of amplifiers. So, amplifiers are controlled sources, either controlled voltage sources or controlled current sources. Now, a voltage amplifier is a voltage controlled voltage source, whereas when you talk about a current amplifier, it is a current controlled current source, meaning in a current amplifier the input as well as the output are both currents. When we come to the third type of amplifier, the transconductance amplifier, it is a voltage controlled current source, meaning the input is a voltage whereas the output is a current. Now, the last type of amplifier is called a trans resistance amplifier, which is also called a current controlled voltage source, meaning the input is a current and that current controls the voltage source, the output is a voltage. Now, most of the time we are talking about a voltage amplifier. Let us see the equivalent circuit of a voltage amplifier. Now, essentially voltage amplifier can be shown by the figure which is shown here. At the input side you have a resistance Ri, which essentially models the input resistance of the amplifier, and the voltage which is to be amplified Vi develops across that particular resistance. Now, the output side you have a controlled voltage source whose amplitude is AVO times Vi, and AVO meaning the open circuit voltage. Now, being a voltage source, it is represented as a Thevenin equivalent by its Thevenin equivalent model. So, you have the open circuit voltage and in series with a resistance R naught, which is the output resistance of the amplifier. Now, since voltage amplifier is the most commonly used amplifier, let us look at what are some of the requirements. Now, we would connect an input to the voltage amplifier, and what we want is the entire voltage should develop across Ri, which means that this Ri, the input resistance here, must be as high as possible. Ideally it should be infinite. Now, the voltage gain could be as we require. Now, coming to the output resistance, that resistance should be as small as possible. Since it is a voltage source, the resistance should be as small as possible, because any load, when you connect a load across the output, any current which flows into the load would develop a voltage drop across R naught. So, ideally the output resistance should be 0, and again bandwidth as required. So, when we talk about a voltage amplifier, ideally we would like to have infinite input resistance and 0 output resistance. Let us look at one more amplifier, the current amplifier. Now, the equivalent circuit of the current amplifier is shown here, where again you have an input resistance Ri. We would like the entire current from the input to flow through Ri, and the output being a current source, it is represented by the Norton equivalent, and we have an AIS I, whereas where AIS is the short circuit current, and R naught, which is the output resistance of the current source. Now, coming to the ideal characteristics of a current amplifier, since we would like the entire current, input current to flow through Ri, ideally the input resistance should be low, ideally it should be 0. Coming to the output side, since we would like the entire current to flow through the load, R naught ideally, the output resistance R naught ideally should be infinite. There is a very common misconception that for every amplifier the input resistance should be infinite. This particular equivalent circuit of the current amplifier shows that that is not so. We need to look at the particular amplifier in question to decide what its input and output resistance should be. If the input is a voltage source, it is a voltage controlled, then we need to have infinite input resistance. If it is a current control, then it should have Ri 0. Most of the time when we talk about an amplifier, we actually mean a voltage amplifier. This is because most of the time we require a voltage amplifier, and the reason is most of the sensors give a voltage output, and we more often come across voltage signals than current signals. However, there are applications where you might come across currents as well. Let us take the example, let us take an example to illustrate the requirements of an amplifier and to set the context for today's lecture. Let us think about a public address system. Right now I am speaking into a microphone, which may be a condenser microphone in this case, or it may be in some cases a dynamic type microphone. So the signal at the output of the microphone need to be amplified, and you would have a preamplifier in the public address system and followed by a post amplifier, and finally you would have an output stage or a power amplifier, and the signal then flows into a loudspeaker. So this is a good example to consider the amplifiers and the typical requirements of amplifier. Now when we look at an ideal voltage amplifier, we studied last week that an op amp almost, you can think of an op amp as an almost an ideal voltage amplifier. This is because of the reason that when you use negative feedback in an op amp circuit, and especially if you think about the non-inverting amplifier circuit, you would see that the input impedance is very high, which is a requirement for a voltage amplifier. And again, because of the negative feedback, you would see that the output resistance is extremely small, again what is required of a voltage amplifier. However, when we think about an op amp, very often we think of op amps as ideal blocks, but there are a few disadvantages which op amps have, general purpose op amps have. Let us look at 741. Now 741 and other general purpose op amps cannot be used for applications beyond about 10 kilohertz. This is because of the slew rate limitation, which happens because of the compensation, internal compensation provided in an op amp. So therefore, most of the time you cannot use a 741 for applications beyond 10 kilohertz. Then somebody might ask, then what is the use of an op amp? Interestingly, most of the sensor outputs, the frequencies do not exceed about 1 kilohertz. There are very few sensors which would give you signals beyond 1 kilohertz. So therefore, when 741 or other op amps were made, the manufacturers had that in mind. So they know that for the 95% of the applications you could use a simple op amp and have an ideal case. There are op amps which can be used for high frequency applications also, however they are very costly. Now let us come to the case of discrete amplifiers. Now common emitter amplifier is an example of a discrete amplifier. Now, when you think about a discrete amplifier as compared to an IC amplifier like 741, a discrete amplifier can be tailor made as per our need, especially as we said the frequency response of an op amp is very small. We could actually make a discrete amplifier to meet our requirement, and most of the time discrete amplifiers would not be very complicated and they are easy to build and also analyze. However, since there are many components and they need to be assembled either soldered or made into a PCB or into a breadboard, the reliability of discrete amplifiers is very low. Another very important thing to keep in mind is discrete amplifiers need to be biased and designed very carefully. Also, in a discrete amplifier, the gain and other amplifier parameters are device dependent. If you compare this with an op amp amplifier, you would see in an op amp the gain is independent of the device parameters, whereas in a discrete amplifier most of the time you would see that even when negative feedback are applied, only an approximation we can take the gain to be independent. When we talk about BJT based discrete amplifier voltage amplifiers, we have three amplifiers. One is the common emitter amplifier, which is the most commonly used. We will see a bit later why. Then you have the common base amplifier, and you also have the common collector amplifier. Now, in my last lecture last week, I had mentioned the meaning of the word common. When you say common emitter amplifier, what we mean is the input signal is applied between the base and the emitter, and the output signal is taken between collector and emitter. Hence, emitter is a common terminal, and most of the time it is at ground potential, and hence the word common emitter. In a common base amplifier, the base terminal would be most of the time almost at ground potential, and the input will be applied between emitter and base, and the output will be taken between collector and base terminals. In a common collector amplifier, collector would be the common terminal and collector would be at AC ground potential. Input would be applied between base and collector, and the output would be taken between emitter and collector. Now, let us look at common emitter amplifier in some detail. Now, the first thing we need to consider when we talk about a common emitter amplifier is to have an idea about the output characteristics and to decide how you go about. Now, as I said my just right now, one of the most important things about a discrete amplifier is that you need to bias the device, in this case a BJT, in the proper with a proper operating point. Now, what we have here is the Icbc characteristics, which is also called the output characteristics. On x axis we have VCE, and on the y axis we have the collector current IC. Now, the output of a common emitter amplifier would be VCE voltage. Now, as we know from this characteristics, we see that the extreme left side we know is the saturation region, and when you talk about an amplifier, we are talking about a linear application. Hence, we should not, the transistor should never get into the saturation region. So, we should choose an operating point somewhere in the middle. Also, we should ensure that the transistor never goes into the cutoff, which is the towards the x axis. So, you would choose somewhere in the middle. Another very important consideration when you talk about a discrete amplifier is what is called the signal swing. Now, what we essentially do, assuming this particular point here as the Q point or the quiescent point or the operating point, Now this particular point you have a certain base current, and corresponding to that you have a collector current and you have a VCE voltage. Now when we apply an input to the base, the voltage which we apply gets superimposed to the DC voltage, and the base current increases and decreases in accordance with the input signal. As the base current increases and decreases, correspondingly the collector current decreases and increases. Now corresponding to that, the voltage VC voltage would change, and later we see we would have a resistance RC, collector resistance, and we need to ensure that we need to choose this resistance value at the operating point such that even for the maximum signal swing we are far away from the saturation region and the cutoff region. If not, the output signal will be distorted. So one of the first things we do in a discrete amplifier is to do a proper biasing. So we need to choose an appropriate operating point, thereby we are actually choosing a IC value and a VC value on this particular ICVC characteristics. Now as I said, we need to ensure that we keep away from both saturation and cutoff regions. Now when we talk about biasing circuits, there are a few other considerations as well. Now we need to make sure that the small VB variations which occur because of temperature variations should not upset our operating point. So we need to make sure that the circuit can take care of small VB variations. Another important consideration is, in a discrete amplifier, since we are using discrete components, the beta value of BJT of the same type would vary very much, sometimes as much as 50%. If you pick a BC147 transistor and measure its beta, and you go to the market and buy 10 such transistors, and if you measure the beta, you will be very surprised to see that there is large variation of beta, sometimes as much as 50%. Hence we need to make sure that the circuit is able to tolerate large variations in the value of beta. What we have here are two bad biasing circuits. Let us see why they are bad. This first circuit, what it does is, it essentially establishes a DC VB voltage using a potential divider, and it assumes that once you do that, the operating point would be stable. Now the emitter is grounded here. Now what happens is, in case of any temperature variation, ambient temperature variation or junction temperature variations, we know that the VB has a negative temperature coefficient of 2 millivolt per degree centigrade rise. So if for some reason the temperature rises, and then what happens is, we have a fixed value of VB at the potential divider, but the VB value, because of the increase in temperature, the VB required for the same current which we had is now less, or equivalently, since the VB value is because of the temperature negative temperature coefficient, the current now increases. Now once the current increases, we would have another increase in temperature, junction temperature, which would again make the VB to again decrease, and then we have what is a process called thermal runaway, which essentially would make the circuit, essentially that is a name given for unstable biasing condition. So we see that this circuit is not suitable, it is a bad biasing circuit. Now the second circuit here, what we have here what is done is, a resistance RB is connected between VCC and directly to the base here. Now, what is aimed here is to have a fixed value of IB by choosing an appropriate value of RB. And as we said, there is large variation of beta between different discrete transistors. So, if you do this, what will happen is what we designed may not be what we get. The collector current which we desired we will not get. Hence, these two circuits are not suitable. Now, what is commonly used is the biasing circuit, which is also used in RC coupled amplifier, where we have a single power supply, a voltage divider at the base, just like the previous case, and the difference here is now we have added a series emitter resistance here. Now, the emitter resistance here has a very important role. We said in the previous case this emitter resistance was 0. Therefore, what happened was whenever there was a temperature variation, when the VB changed and when the current changed, that resulted in something like a positive feedback. In this case, what happens is if the same thing happens, that is why what we mean, if the temperature increases and if the VB value decreases and the current increases, what is going to happen is, since we have a resistance here, the emitter potential now will rise. Now, with this rise in emitter potential, the VB would now reduce. What we assume is that the increase in current does not change the VB, the base voltage, which can be satisfied by choosing R1 and R2 appropriately. So, what happens is whenever there is a temperature variation and the VB value decreases, that effect is countered by the emitter resistance here, and a kind of a negative feedback comes into picture, and that opposes this. Because of this, the biasing point would be quite stable, and also we need to make sure that for large beta variations also this particular circuit works. Now, this can be taken care of by choosing R1 and R2 quite small. Now, what we do is we need to ensure one thing is to ensure that small VB variations are not upset. We need to make sure that the voltage here, the VBB voltage, which is the voltage at the potential divider, should be much higher than what is the required DC VB value, and we need to make sure that the RE value, the resistance at the emitter, should be greater than RB by beta plus 1. We will see how we ensure this. So, as a thumb rule, what we generally do is to ensure stable biasing and also to ensure that the operating point stays somewhere in the middle of the characteristics. What we do is we choose the VBB, which is the voltage, the base potential, VCE and ICRC, the drop ICRC. We take all these three to be roughly 1/3 of the supply voltage, and to ensure that beta variations do not upset, we approximately we could take the current through R1 and R2, the current flowing through R1 and R2 to be approximately 10% of the current IE, the emitter current. Now, the reason for doing this, you can think of this in another way. Now, the base current is much smaller than the emitter current. Now, what we need to make sure is that the current flowing through R1 plus R2 should be much greater than the current flowing into the base. If we can do that, then beta variations will not upset. So, this is the circuit which is commonly used. Now, for tomorrow, your lab for tomorrow afternoon's lab, you have the common emitter amplifier, and the same rules you would be applying. So, what we discussed today can be implemented. Now, before we talk about the, so we now saw the biasing and we saw how to choose biasing. Now, before we talk about the BJT amplifier, common emitter amplifier model, one very important thing we need to keep it in mind is what is called the small signal approximation. You might remember last week in my lecture we talked about the Ebert-Small model, and there we used the term large signal model, and we said using Ebert-Small model we could get DC currents or large values of currents for any value of base emitter and base collector voltages. Now, in an amplifier, one of the most important thing we need to keep it in mind is that it is a small signal application, meaning a BJT, as we see from the characteristics, as we know from the BJT characteristics, is a nonlinear device. We need to operate, we need to ensure that our application, amplifier application is a linear application. So, we need to make sure that the variation in the VB value is much smaller compared to the VB, the DC VB. So, generally what we do in any circuit, if you look at the instantaneous VB value, it would have two components. One would be the DC VB value, which we obtain by choosing an appropriate biasing circuit, and an AC VB, which is our signal. Now, in the small signal approximation, what we mean is the signal which we apply, VB, should be much smaller than VT, which is the thermal voltage, approximately 25 millivolts. So, typically we are talking about the small VB to be in the order of about 10 millivolt. If we do not have signals as small as 10 millivolt, what would happen is there will be distortion. Most of the time we may not be able to appreciate distortion when we see it on an oscilloscope, but if we use a signal analyzer, then we would see that there is distortion. For that matter, any amplifier has distortion. There is not a single amplifier which does not have. All that we can do is to reduce the distortion. So, if we keep the VB value as small as possible, say less than 10 millivolt, then we can get reasonably good amplification without much distortion. Now, before we look at the common emitter amplifier, let us look at an appropriate model. Now, the most commonly used model and fairly accurate model for analyzing a BJT amplifier is what is called the hybrid pi model. Here, let us look at the conceptual circuit and the model. What we have here is a common emitter amplifier, and this is what is called a conceptual diagram. This particular diagram has no biasing, because only the AC signals are shown. So, that is why you find a short circuit here. Now, for as far as AC is concerned, a battery is a short circuit. You can think of, since the battery voltage does not change, we can, for as far as AC is concerned, it is a short circuit. And we have small VB as the input here, and that causes a small IB current flowing into the base, and that would cause a collector current. Now, in the hybrid pi model, the input circuit base to emitter, we have a resistance R pi, which is essentially small VB by IB. The small IB would give you R pi. Now, the other parameter here is GM, and GM is IC by VT. IC is our DC current, biasing current, and VT is thermal voltage. So, once we are able to finalize our biasing circuit, once we determine our IC, we can get GM. Now, GM and R pi are related through beta. So, once we know what is GM, we can find R pi also. So, once we have that, we can get the hybrid pi model. Now, this particular model, what is shown here, neglects early effect. Now, if you remember, when we talked about early effect last week, we said early effect is basically it is about variation in the collector current as a function of the VCE, the collector to emitter voltage. Now, in a hybrid pi model, early effect can be modeled by putting a resistance across the current source, and that resistance R0 is defined as early voltage divided by IC. So, we see that once we complete our biasing and once we are able to determine the value of IC, we can determine all the small signal parameters, that is GM, R pi and R0. So, we are, once we do this, we are at a position to analyze the amplifier circuit. Now, before we analyze our common emitter amplifier, we need to look at the amplifier parameters a bit more carefully. We talked about input resistance, we talked about voltage gain, we talked about output resistance. Let us define them properly. What we have here is a block schematic of an amplifier, and what we are shown here is the input signal represented by the Thevenin equivalent, an open circuit voltage V sig and a Thevenin resistance R sig, and a current I flows into the amplifier, and at the input of the amplifier a voltage Vi develops, and from the output a current I0 flows into the load RL, and across RL we develop the output voltage V0. Now, the definitions, the parameter definitions for an amplifier are as follows. Input resistance with no load is defined as Vi by Ii, that is for RL equal to infinity. Now, input resistance R in is defined as Vi by Ii with RL in place. We will come to this in a minute. Now, you might remember when we modeled the voltage amplifier, we had an open circuit voltage called AVO. Now, that open circuit voltage gain, which is the voltage gain, is defined as V out by Vi with RL infinity or without RL here, and normal voltage gain is V out defined as V out by Vi with RL in place. Now, coming to output resistance, it is a bit more tricky. What is generally done is we would apply in a simple circuit, it is very easy to determine the output resistance, but in complicated circuits what we would do is we would connect a voltage source called Vx and connect that to the output side and find the current flowing Ix. If that is the case, output resistance R0 will be Vx by Ix at Vi is equal to 0, which means the input to the amplifier, that side should be shorted. Similarly, you have another definition of output resistance R out, which is defined as Vx by Ix at not Vi is equal to 0, but V sig is equal to 0. Now, in the previous case, the assumption is that your R sig is 0, equivalent to saying R sig is 0, but in a general case the series resistance of the source may not be 0. So, you would make R V sig 0, which means you would have the effect of R sig. Now, it may be confusing why it's quite confusing to see why we have two sets of input resistances and two sets of output resistances. Now, to understand that, we need to talk about what are called unilateral amplifiers. Now, when you talk about an amplifier, certain types of amplifiers are called unilateral amplifiers. Now, in these amplifiers, the input resistance does not depend on the load resistance, that is, there is no output to input internal feedback. So, in a unilateral amplifier, Rin will be the same as Ri, and R out would be the same as R naught. Many amplifiers are non-unilateral. Now, let us look at common emitter amplifier. Now, as we said, one of the first things we need to do is to choose the values, the biasing circuit carefully. That is, we would choose R1 and R2 carefully, we would choose RE and RC, we would these resistors would be chosen such that we have ICRC approximately 1/3 VCC, and we have a VB voltage of VBB voltage of 1/3 VCC and a VC of 1/3 VCC. Now, what we have drawn here is the common emitter amplifier. Now, we have the signal source here VSIC and an RSIC here. So, in general it is always better to keep the Thevenin equivalent resistance of the voltage signal source. Now, this is connected to the common emitter amplifier through a capacitor. Now, why do we need this capacitor? Now, what will happen if I do not connect this capacitor? Now, we see that we have chosen R1 and R2 so as to establish a certain DC bias here. Now, if we do not connect this capacitor, what is going to happen is we are going to have this resistance and this voltage source also coming into picture. This will completely upset our biasing and the transistor will not work. Now, most of the time this capacitor which we have here would be of the order of tens of PF or a few PF, sorry, a few microfarad. So, typically let us say 10 microfarad. Now, again, how do we choose the polarity? Now, 10 microfarad corresponds to a electrolytic capacitor which has polarity. Now, how do we decide the polarity of this capacitor? Now, in such cases what is important is we need to look at one of the sides of the capacitor where we are sure about a certain voltage. In this case, we see that this capacitor, the base side has a certain positive voltage, whereas this side we are talking about an AC. So, it is almost 0 here. So, the capacitor would have a positive polarity towards the base side and negative polarity towards the signal source side. Similarly, we have a capacitor here at the output side, and that is connected to the load here, RL here. Again, why do we need a capacitor here? Now, if you remember, when we talked about biasing, we said we would choose the biasing point based on R1, R2, RC and RE, which means that if I do not have this capacitor, the moment I connect RL, once again this value of RL will disrupt my biasing. So, for the same reason I need to have this coupling capacitor C2 here. Once again, how do I decide the polarity of C2? Now, here again the same principle, we need to look at the side we are sure about the polarity. Now, we know that the collector side of the capacitor has a higher positive voltage, whereas the load side is connected to ground. So, we would choose a positive polarity on the collector side and a negative polarity of the electrolytic capacitor on the load side. Once again, typically the value of C2 would be about 10 microfarad typically. Now, we can have two types of common emitter amplifier depending on whether we have a capacitor connected between emitter to ground or not. Now, in the first case, the most common case, we would have a capacitor CE connected between emitter and ground. Now, in today's lecture, we will not look at the details of the low frequency response. Now, what we see is that when we do the analysis, we would see that the value of CE would be much higher compared to C1 and C2. Typically CE would be the order of about 100 microfarad or around 50 to 100 microfarad. Here again the polarity is quite straightforward. Towards the emitter you would have positive polarity for the electrolytic capacitor and the ground negative polarity. Now before we start analysis, one very important thing to keep it in mind is that we are talking about mid-band frequency analysis. Again, what do we mean by mid-band? We can draw the frequency response of a common emitter amplifier, the one which I showed just now, something like this. Now we see that the amplifier characteristics we see is like a band pass filter. It has two cutoff frequencies, and let us call the first one the lower cutoff frequency and the upper one as the upper cutoff frequency. Now we have a region in the middle which is called the mid band. Now the frequencies below FL, the lower cutoff frequency, you have a high pass response, whereas frequencies above FH, the upper cutoff frequency, we have a low pass response. Now what is the reason for the high pass response? Now we can see that these coupling capacitors and the CE, so these three capacitors contribute towards the low frequency response of the amplifier. So we, depending on the kind of value of the low frequency cutoff we require, we can choose appropriate values for C1, C2 and CE. Similarly, when we talk about the upper cutoff frequency, now that is a region which is due to the device capacitances. This we will see a little later. Now when we talk about mid band frequency is the region where the frequency response is flat or the gain is constant. So we assume that in this particular region the coupling capacitors as well as CE are short circuits, their impedance are negligible, so they are short circuits, and the device capacitances are open circuits. So when we talk about an AC analysis, we are talking about the mid-band analysis. Now again let us look at the equivalent circuit and try to get some expressions for the amplifier parameters. Now R in we defined as Vi by Ii. Now in this particular circuit here we see that the Ii is the current flowing, Vi is the voltage across Rb. Therefore the input resistance R in is nothing but Rb parallel to Rib. Now Rib as we see here is nothing but R pi, which we would have determined, and we know that Rb is generally quite high compared to R pi. R pi would be typically of the order of 1 kilo ohms or so typically, or sometimes even less, depending on the value of the collector current and the beta. Now so therefore we see that the input resistance R in is approximately R pi, which means the input resistance of a common emitter amplifier is approximately 1 kilo ohms of kind of that order. Now when we talk about Vi, that is the voltage at the input of the amplifier. Now our signal source is V sig. Now if you write an expression for Vi in terms of the signal source V sig, we can write Vi as V sig times Rin by Rin plus R sig. Now we know that Rin is equal to Rb parallel R pi. So substituting, we will get this as V sig into Rb parallel R pi divided by Rb parallel R pi plus R sig. Now we said that Rb parallel R pi is approximately equal to R pi, therefore we can write Vi as approximately V sig times R pi by R pi plus R sig. Now we see here that when we use a common emitter amplifier, if we have R sig significant in comparison to R pi, then we are going to get a much smaller fraction of the input voltage developed here. So in this case we see that V pi is same as Vi here. Now coming to the output side, we can see that the voltage V out here is nothing but the current here times R naught. I have not shown here RC, so should have been an RC also here. So R naught parallel RC parallel RL. So I am with a minus sign because the current is flowing towards the away from the output towards the ground. So the output voltage is minus of Gm V pi into R naught parallel RC parallel RL. Now the voltage gain AV with load then would be V out by V pi or V out by Vi, which is nothing but minus of Gm R naught parallel RC parallel RL. Now if you assume RL is equal to infinity, you would get the open circuit voltage gain, which would be minus of Gm times R naught parallel RC. Most of the time R naught, which is the output resistance which we put, which models the early effect, most of the time would be quite high. This is especially for discrete amplifiers. This is because of the reason that VA, the early voltage for most of the transistors, could be of the order of about 200 volts. So if you are talking about 1 milliamp and 200 volt, then R naught is much higher. So most of the time you would find that the output voltage, open circuit output voltage, is nothing but minus of Gm times RC. Now coming to the output resistance, it would be nothing but R naught parallel RC, or we can say, as we said, R out would be approximately equal to RC, since R naught, small r naught, will be very high. Now another very important parameter is what is called the overall voltage gain, which measures from end to end, that is from V naught to V sig. Now that we can get as Vi by V sig times into V naught by Vi, which will be nothing but Vi by V sig times AV. Now if we assume that the resistance of the signal source R sig is much smaller than R pi, then we see that the overall voltage gain is approximately equal to the voltage gain. Now this is an extremely important parameter to be important point to be kept in mind, and we see here a major disadvantage of the common emitter amplifier. Now most of the time when we do an experiment in the lab, the signal source would have a resistance R sig of the order of 50 ohms most of the time. Now the R pi, I said, it will be the order of somewhere around 1K to 2K. So therefore we would see that whatever calculations we do, we will be able to see that we get the same value. But if we use a common emitter amplifier directly for, let us say, for a sensor application, we would see that we get much smaller voltage gain, and the reason is the large value of R sig. This is something which is very important to be kept in mind. Now I would tomorrow, the lab, you have a BJT amplifier circuit, and there is a detailed design procedure is given there. So I would request all of you to go through the example there, and you could, all the equations are also given in your lab handout. You could work it out, and in the lab you can check carefully. And as I said, when you wire the circuit, a few things you need to keep in mind carefully. One thing is to connect the transistor correctly. The collector, base and emitter terminals will be correctly connected. And we know, since we talked about the reverse active mode and the normal active mode, if you interchange emitter and collector, we know what will happen. You will get much smaller beta, and therefore it's as good as the transistor having no gain. So next time you don't get a proper gain, it's quite likely that you have interchanged the collector and the emitter terminals. So keep that also in mind. And before you come to the lab, do some hand calculations using the equations given in your handout and also in this, and then you could compare that with the values you get. Now, the previous example of the common emitter amplifier, we use the hybrid pi model to analyze it. There is another model called the T model. This particular model is useful in some situations. We will see which situations where this is convenient. Now, the hybrid pi model is useful whenever your emitter is at ground potential. Like in the common emitter amplifier with a CE connected there, we know that the emitter is at ground potential. In such a case, the hybrid pi model is very simple. But in case if you have a situation where your emitter has a resistance to ground, then the hybrid pi model would be quite complex. In such a situation, this model T model would give you very, very simple solutions. Now, what this T model has is, it has essentially a voltage controlled current source model, something similar to what we used in the large signal model in the last week's lecture. So, you have an IB here, you have a VB voltage developed across a small RE, and you have a controlled current source which is GMVB. This value was same as the value we had in the hybrid pi model. You also have this was a voltage controlled current source model, whereas here it is a current control. Now, in this case, the only difference is the controlled source has alpha times IE. So, the controlling parameter is IE here, and you have a small RE. And in this model, you need only GM and small RE, and GM we know is IC by VT, and small RE is defined as VT by IE, the emitter current. So, once again, this would be nothing but alpha by GM. So, once we know the biasing, the operating value and the biasing conditions, we can determine these values also. Now, let us analyze now the common emitter amplifier with an unbypassed series emitter resistance. You have this in tomorrow's lab also, and once again we could analyze this. So, the only difference between this particular circuit and the circuit which we saw just before this is that here the emitter is unbypassed, which means there is no capacitor from emitter to ground. Otherwise, you have the coupling capacitors C1 and C2, which we said are must, otherwise the biasing will get upset. Now, what we have done here is we have used the T model here, and we can see here, and in this case it gives you an extremely simple equivalent circuit, and in fact this will be much simpler. You could use hybrid pi model also, but you would find that the expressions would be much more complicated. Now, in this case we have connected the V sig here, you have R sig here, you have RB here, and then between these 3 points here you have connected the transistor. You have between emitter and ground you have RE, which is the resistance there, and you have small RE, which is a small signal parameter, and you have a RC there coming from between collector to ground, and RL. Now, once again we can determine what is R in here, which is nothing but VI by II. Again, R in is RB parallel RIB. Now, compared to the previous case when we had a capacitor between emitter and ground, here you would see that RB RIB or the resistance looking into the base is quite different. In this case RIB is Vi by IB, and IB we know is IE by beta plus 1, and IE we see, since we have Vi here, the same Vi is appearing at this particular terminal also. Therefore, IE can be easily calculated as Vi by small re plus capital RE. Therefore, IB would be Vi by beta plus 1 times B RE plus capital RE. Therefore, RIB would be beta plus 1 times small re plus capital RE, and Rin therefore would be RB parallel RIB, which will be RB parallel beta plus 1 small re plus capital RE. Now, most of the time we would choose RB such that it is much greater than RIB. So, we see that if we can do that, if we can choose RB to be very high, then we would see that just by increasing RE, we would see that the input resistance of the common emitter amplifier without a emitter bypass capacitor will be very high. If you remember, in the previous case our main minus point was that the input resistance was very small. So, in this case we would see that there will be a substantial increase in the input resistance. However, there is one thing we need to keep it in mind. There is a limit to which, up to which you can increase RB. We know that if you increase RB too much, then we would have the problem of the biasing circuit becoming unstable due to beta variations. So, we see a typical design situation here. In any engineering design we have trade offs. So, we see a simple common emitter amplifier circuit design also giving you this kind of interesting features. So, the input resistance of a common emitter amplifier without a emitter bypass capacitor would be very high. Let us look at the voltage gain. Now, the voltage gain in this case would be V out, V naught will be minus of IC into RC parallel RL. Now, in our analysis here we have removed small R naught, which was modeling the early effect for simplicity, and we said last time also that R naught is for especially for a discrete amplifier, R naught, small R naught we said is very high. So, we could, so if you do that, then we see that V out is equal to minus of RC, RC parallel RE, and if you substitute for RIC, IC would be nothing but alpha times IE, and we know that IE is equal to Vi by RE plus capital RE. Therefore, AV, the voltage gain with load, we can write as V out by Vi equal to minus of alpha RC parallel RL divided by small re plus capital RE. This will be approximately, if you assume alpha to be 1, then this will be approximately minus of RC parallel RL by RE plus RE. Now, most of the time small re would be a very small number, typically say about 25 ohms or 50 ohm in comparison to capital RE. So, we would see that the voltage gain of a common emitter amplifier without an emitter bypass capacitor, you see that would be RC parallel RE divided by approximately RC parallel RL divided by RE, which would be quite small. Again, you could try the lab handout given to you and you could work out these numbers. So, we see that what in this particular case what we have is actually a negative feedback, and when we talk about negative feedback in one of the later lectures, we will see whenever we apply negative feedback, the price we pay is the voltage gain. In fact, we trade off voltage gain for other useful parameters. So, in this case, by getting a much lower voltage gain, we got in return a much higher input resistance, and also we would see that you will also get much higher frequency response. And in this case, the output resistance R out will be RC, Now, another important thing to keep in mind, both for this particular amplifier we considered now, and also the amplifier we considered the common emitter amplifier with a emitter bypass capacitor, is that in both the cases they are unilateral amplifiers. And as we said, when we say unilateral amplifier, what we mean is that these are amplifiers where we assume that anything we do at the input does not upset the output, meaning if we change the input signal source, and that R6 value will not change the output resistance. Similarly, whatever we do at the output should not upset the input, which means if you change the RL load resistance, then that should not change the input. So, in a unilateral amplifier, Rin will be same as Ri. Now, in this particular model, we assumed we did not have the device capacitor, therefore, our approximation of a unilateral amplifier was correct. Now, let us compare these two amplifiers, the common emitter amplifier with an emitter bypass capacitor and the common emitter amplifier without an emitter capacitor. Now, in one case we saw that the amplifier with an emitter resistance, which is generally called the degeneration resistance, we saw that the input resistance increases, but we saw also that the voltage gain will get reduced, but the advantage of the voltage gain expression we saw there was that the voltage gain expression was much less dependent on beta value, and also because of the negative feedback, the other parameters of the amplifier also improves.